All right. Hello, everybody, and welcome to another episode of Advent of Code in Kotlin. Hey, everyone. Hope you had a good time joining, hopefully, the previous webinar that we just had with Pamela and Martin. If you're coming from there, please let me know. And also in general, it's good to see you. I'm sure our music is going to kick in a second here. Exactly. Very good. Those are the vibes that we need. And also, let me know how on this very wonderful Advent of Code in Kotlin day 3 you felt about the puzzle. I feel like they're starting to ratchet up that difficulty step by step. So, yeah. And of course, today we're going to have another lovely journey with a little bit of tea, a whole lot of puzzling, a wonderful guest. As part of our Advent of Code campaign, it is day 3 by now. So most of you will probably already know what's going on, but I see that there's at least one person in chat here who is new, so you'll still get the full explanation. Let me just hop on over here, because we are solving Advent of Code algorithmic puzzles every day, well, for the first 5 days of this challenge, so Monday through Friday, and we're doing this as part of our Advent of Code in Kotlin campaign. Recurring viewers will have noticed that I've taken the advice that I've gotten from recent days, and we no longer have a white background on when I show off the blog post. So hopefully, to all of you who are already cuddled up by the campfire and in a dimly lit environment, I will no longer be burning your eyes out with a completely bright page. Exactly. No more blinding white. As part of this campaign, we are doing, of course, the live streams, but there's a couple of other things that you should be aware of. First of all, since there is no public leaderboard anymore, we do still have a couple of community leaderboards for the Kotlin community. You can join those, and you can see how quickly you perform or how well you perform. And even if you're not particularly interested in the speed challenge, it is still very much worth joining there, as well as checking out the blog post in general, because there's a couple of other things that you can do that are illustrated here that allow you to win some cool Advent of Code prizes. So make sure you check that out. If you're just getting started and you would like to get a little bit of a scaffold for how you might set up a project, I will, of course, once more refer you to the Advent of Code in Kotlin template. This one is also linked here as well. And it also gives you a nice little starting point. Okay, so before we dive in, let's see if we already have a couple of opinions here. We have a little bit of an ordering here. Second day was easier than first day was... Sorry, let's see here. This is... Yeah, it was easier than the first day was easier than the third day. So the third day was the hardest, if I'm reading this correctly. I hope I am. Managed to code golf the solution today. Very curious to see or see where we land on the spectrum of hyper minified versus super verbose. Yeah. Okay. Very good. Personally, yeah, I'm starting to feel the heat a little bit. It was certainly not something that you can just whip up without, turning the brain on for sure. Okay, well, hopefully everybody who's come from the previous stream, from our wonderful KMP webinar, has had time to refill their cup of tea with whatever flavor of their choice and are here, which means we can really get into the main aspect here. And of course, we're not going through this alone. I'm very excited to be introducing my guest for today, who is Maya Grotepas. Here we go. Hello, Maya. How are you doing?
I'm great, thanks, Seb. Thanks for having me on the show.
Yeah, I mean, it's so good to have you back. We've had you on a couple of times as well. So it's always nice to have some familiar faces as part of this wonderful little December ritual that we have going on.
So I have a question for you.
Yes.
Do you think if the difficulty was from 1 to 24 in previous years, and now it's going from 1 to 12, do you think we're about at 6 because we've got on day 3? Do you think it's linear? Hey, Miro.
I think so. I think that's kind of the vibe that I'm getting, because I don't know about you, but this felt like it certainly did not feel like a day 1 through 5 puzzle in the original like 24-25 day length of puzzles.
Yeah, it didn't for me either, and it wasn't very compatible with a day job.
Oh yeah, that's the trickiest part.
Yeah.
And I mean, add to that the bonus of, if it's if you're just doing it for fun, then there's no harm, no foul. But when you're scheduled to come on a stream, there's just this little extra tiny little bit of extra pressure of saying like, well, now I really gotta go for it, or yeah, now there should be a nice answer.
So there is a possibility that I didn't get the second answer.
I mean,
so we'll have to see. We'll have to wait and see. We'll have to wait and see when I open my code to see if I got the second answer or not.
Oh, okay. Very, very interesting. Well, sounds dramatic. Yeah, we also have the assessment here. Yeah, today we're at day 6 and the difficulty is jumping. Mr. Wastler won't have the difficulty level just because there are 12 days. Yeah, that's getting compressed for sure. So we'll really see. I feel like by the end of the week we'll have already covered quite a lot of ground problems wise. Should be interesting. Okay, let's actually head into the problem and see what was going on. I gotta throw on the hat here. Oh, what is that? Ooh, another hat I spot. Wonderful. I love the preparedness. Oh, it's so shiny too. That's a great hat. Is that illuminated? Does that have like a...
It's got shine, it's got like glitter, and if we manage to solve the problem, I can make it change color.
Oh, that's incredible. That's wonderfully festive. Love to see it. Love to see it. Well, that can only mean good things. So let's dive in with day 3. Lobby. You descend a short staircase, enter the surprisingly vast lobby, and are quickly cleared by the security checkpoint. When you get to the main elevators, however, you discover that each one has a red light above it. They're all offline. Sorry about that, an elf apologizes as she tinkers with a nearby control panel. Some kind of electrical surge seems to have fried them. I'll try to get them online soon. You explain your need to get further underground. Well, you could at least take the elevator down to the printing department. Not that you'd get much further than that without the elevators working. That is, you could if the escalators weren't also offline. But don't worry, it's not fried, it just needs power. Maybe you can get it running while I keep working on the elevators. There are batteries nearby that can supply emergency power to the escalator for just such an occasion. The batteries are each labeled with their joltage rating, a value from 1 through 9. You make a note of their joltage ratings, your puzzle input. For example, 9, 8, 7, 6, 5, 4, 3, 2, 1, 1, 1, 1, 1, 1, 1, 8 1 1 1 1 1 1 1 1 1 1 1 1 1 9. That's a lot of ones. 2 3 4 2 3 4 2 3 4 2 3 4 2 7 8 and 8 1 8 1 8 1 9 1 1 1 1 2 1 1 1. Best part of the entire job. The batteries are arranged into banks. Each line of digits in your input corresponds to a single bank of batteries. Within each bank, you need to turn on exactly 2 batteries. The voltage that the bank produces is equal to the number formed by the digits on the batteries you've turned on. For example, if you have a bank like 1, 2, 3, 4, 5, and you turn on batteries 2 and 4, the bank would produce 24 jolts. You cannot rearrange batteries. You'll need to find the largest possible joltage each bank can produce. In the above example, in 9, 8, 7, 6, 5, 4, 3, 2, 1, 1, 1, you can make the largest joltage possible 9, 8, or 98, by turning on the first 2 batteries. In 8, 9, you can make the largest joltage possible by turning on the batteries labeled 8 and 9, producing 89 jolts. In 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4, 2, 7, 8, you can make 78 by turning on the last 2 batteries, marked 7 and 8. And in 8, 1, 8, 1, 8, 1, 9, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 1, the largest joltage you can produce is 92. The total output joltage is the sum of the maximum joltage from each bank. So in this example, the total output joltage is 98 plus 89 plus 78 plus 92, which is 357. There are many batteries in front of you. Find the maximum joltage possible from each bank. What is the output joltage? And we can take a brief look here at kind of what our input looks like. Kind of long lines and a whole bunch of lines. So, Maya, what were your thoughts?
Well, the first thought was that 9 is bigger than 8, right? And 8 is bigger than 7.
Yeah.
So I need to start from the 9s. And 9 with anything after is always going to be bigger than 8 with anything after. So the trick is then to find the 9s and work my way down, except for the 9s that are sitting on the edge, because they can't get it. They will just be the units 9, not the tens 9.
Mm-hmm.
So I basically pulled each of those lines, those banks, and figured that out. I had quite a convoluted way of figuring out where the indices of each of the numbers were, and then used that to solve the problem.
Okay, yeah, very, very good. There was another observation here that they are apparently each 100 digits long.
Yes.
And no zeros. That one should not come as a surprise because it does say 1 through 9. Okay, very good. Let's shall we take a look at your code and see what you came up with? Very good. I'm gonna be putting your screen on here. Very good. So
let me see if I can show you. All right, so this is part 1. This is super raw, 6, 7 o'clock in the morning, just writing everything down. I haven't cleaned up anything. So what I will show you here, maybe this is a bit smaller. Here. This is my part 1 here. I have this extension function here, which just pulls out the banks and turns it into a list of integers.
Mm-hmm.
Then I have this method called find max joltage, and I pass each of the banks in it, and then the joltages that come out of it for the maxes, I will just sum them and turn them to a long. This too long is a leftover from my puzzle input. My puzzle structure always uses too long. And so the interesting part here is really this find max joltage part, right?
Yep.
So if I open up find max joltage, I've got this build position lookup thing, which is a map which says 1 to 9 and where are all the indices where the 9s are.
Okay.
Maybe not necessary, but 7 o'clock in the morning, Maya,
Sure.
had a feeling that's what I needed and a weird intuition that I was going to need it later. So if I open this build position lookup, it's using build map.
Okay, very nice.
It's going from 9 to 1, and it's building a list of these indices. So it's taking the map, chasing through it, map index by index here, and then it's just adding the index to the list. And then in the end of this, it's putting this into the map. This is the digit that you want to match, so the 9 or the 8 or the 7. And here there's a list of indices. And for some other reason, I thought maybe I needed them sorted. They are still sorted. So I end up getting this map of all the indices. Then this find max joltage from lookup method, which is over here. Let me open that up for you. It takes this, so it's the bank, but a different representation of the bank. And it starts from tens down to, and a nested loop, unit digits. So it's chasing through the tens digits. It's chasing through the units digit. Not very sophisticated, but hey, it works. These could be inlined, and then let's see where we go. So this is all just null checking over here, and then to see if there are ones for them. And then this is the piece that's the interesting part over here. If any of the tens indices and any of the ones indices, if the tens are less than the ones, then it's a match. And then I return that pair. There's an extension function over here to turn it back and turn int, and it returns that out and it pops out. Okay. So not the best in the world, but certainly delivers the stars, possibly places where it could be golfed, so it's not extremely golfed. And yes,
I think this is quite a that's quite an interesting approach. The approach of first creating essentially a lookup table so that you have easy access to whatever like number you might want to have. That's quite cool. It's quite different from my approach. I'll be honest with you, I'm still very much squinting at the line with the actual condition here. So we
yes. Okay,
yes,
let's see.
Exactly, because
So
it is two nested any's. That's just where I'm getting a little squinting.
Yes. Okay. So I mean, the interesting thing is when I was thinking it up, you know what it's like when you think up the code and you say this is what it is, and you write it down, and then you try and read it the next day. So since this has not been cleaned up, this is certainly a place which is like a little smelly. But let's see, tens indices. So these are all the places where there are the first digit of the two. So say, for instance, you're looking for a 91. It's all the places where the nines are, say.
Yeah. So
okay?
the indices of, yeah. Mm-hmm.
Okay, and then the unit digits. So it will have gone through the first it'll go through 9 and then find all the units. And then here, the unit indices are over there. And what you're seeing is that the tens need to be less than the units. So the tens need to be in position before, because these are indices. The tens need to be in position before the units.
Yeah. Okay. Yeah, that intuitively makes sense. We're trying to find
going
something.
9 down to 1 and 9 down to 1, you're going to get the max. It's implicit in the sense because I'm choosing 9 down to 1. And that's why it's a max, because you're going from the top. So it'll hit 99 before it hits 91.
Yeah, that makes that part makes sense to me. And now that we've walked through it, I think the condition line also very much makes sense, because I think the essential part really, like it really boils down to, you'd like to find a particularly large number for the tens digit, and while still having enough space to also squeeze in like a second particularly large number to the right of it. Like this ordering is the important part.
Yeah, it's the for loops and the fact that you go 9 down to 1. Now, to clean it up, I guess. I mean, there would certainly be readability issues here for me. So this is definitely something that would. But you're getting the raw. You're getting the raw morning puzzle Maya who's chasing the star.
Yeah, no, absolutely. that's the way to go. I think the first and probably the easiest thing that we could do here, right, would be to clear up those nested lets and turn those into like just a continue after, like, using an Elvis operator for each of the actual lookups.
Yes. We could certainly do that. Do you want me to try and see if I can do that now, or we probably won't have time? I might actually break it. So,
I mean, do you have a test? Do you have a test case?
I do have a test. I have a test. Let's see. Well, let's see if the test runs.
Yeah.
We need to see if the test runs in the first place.
I love seeing a little bit of Amper here on screen again. Once again,
absolutely. And yes, my test is in fact green.
Oh, wonderful! So then let's make this small little adjustment. I think that will work well, and then we'll compare it to my solution, which doesn't even look that much different.
Okay, so what would you like me to do? I'm going to be in this is pair programming mode. I'm typing, and you're telling me what to do.
Okay, very good. So in line 40, when we're doing the position lookup, I'd like an Elvis operator with a continue.
Hang on, where's the question mark? Shift like that.
Yep.
Continue.
With a continue, and the same with the line below.
Okay.
And now we see 2 warnings, and I wonder if we can just apply the quick fix directly, and it might just remove the question mark.
Yes.
Is
that what we want though? No, that's not. We want this to go away, right? So we want to use, instead of 10's index, if we do this, right? And this. And then we delete that.
The second one should be units indices, but yes, indeed.
All right. Units, indices. And then I need to delete some of these questions. Oh, this also goes away.
Yep.
Okay, and then we have too many of these, right?
Yeah.
And now
those go away.
Format. Did it format? Yes.
It did. Very nice.
Let's hit the test. We might be able to inline these. Do I use them again? I do use them again. Okay, so better we don't inline. Yes, it still works.
Okay, well, very good. I just really like this as one of the small features in Kotlin. Like, again, it's effectively smart casting at work, right?
Yes.
Another way that one could do would be to use .getValue instead of using the the bracket access operator. But I think yes, but I think like the opinions on whether that's better or not are kind of a little bit split. Because on the one hand, like actually, then we would get an exception, and we probably don't want to do the whole exception handling. So this is
then we need to try catch and do things with the exception.
Yeah. So I think this is a perfectly fine solution. No, very good. And I mean, I think this actually turns out quite smooth, which is quite cool.
Mm-hmm.
Let me show you what I came up with here for this. I'm just gonna rearrange my screen for a second here. And I'm gonna put on my own screen again. Here we go. Very good. I can put ourselves up here. Look at that. And so for part 1, indeed, I do some input parsing, which in my case is literally just reading the line. And I made a lot of the same observations that you did, but I decided to approach the actual looping a tiny little bit different. Because when I thought about this, and they said, well, find the biggest 2-digit number effectively that fits this, I was like, okay, so the best I can get is 99, the worst I can get is 11. So I'm just gonna start iterating those. So instead of having 2 nested loops, I have 1 flat loop, but I still have to break it out into the 10s and 1s. and then I effectively just I'll see. Can I find a 99? Well, I'll see if I have an if I do have a 9 somewhere. If I don't have it, well, then I'll just have to look for the next number. If I do have one, then I will look for the second 9. But specifically here, I'm making use of the fact that the index of function in Kotlin allows you to specify a start index. So here, implicitly baked in, or well, actually explicitly baked in, I say I want to find whatever I have on the ones digit, my second number, to be placed to the right of my tens digit. So if I can find another 9, that's great. If not, I will just have to do another loop. And yeah, so from this, you just check for 90 if you can build a 99, a 98, a 97, and so on. And if I do find one, well, then I just reconstruct that. Which, now that I think about it, I don't even think I need to do this part. I think I can just do the tens digit times 10. Well, I'll still need to do the digit to int conversion here. Actually, what am I think I should just return I, no? Now that I think about it. This looks vaguely correct. Hold on, let me run a test here. Very gives us a lot of suspense. Very good. Okay, yeah, that still passes. Oh, look at it. So amazing. I've managed to. You can tell that I also did this at 6 a.m. There's still some potential there. But yeah, so effectively I just look for a number, and if I can build it, then I just return it. And if I can't find one, then my input was probably broken. So that was my approach.
Yeah, I like it. I mean, it is a little bit more readable for me, although I would have had to figure out a little bit the continues are nice there. I like the continues because it does a similar thing to my one. Mm-hmm. And it all fits into just a few lines of code, which is also cool.
I was very happy to see how flat the structure ended up for this piece of code. This is a like dramatic foreshadowing for part 2. Yeah, for part 1, this seemed quite convenient. I did find it quite interesting that for this problem, it really seemed like a lot of it for me was just like squinting at the problem and being like, if I were to do this manually, like how would I do it? I'd be like, well,
yeah,
just find me the 9s. If I can't find them, just find me a 9 and an 8. And if I can't do that,
yeah. So I mean, for me, it was a similar thing. It's like staring at it and seeing. And at one point, I was also searching how many 9s do I even see in the whole of the pattern, or how many of them are there. So how heavy is it going to be if I'm looking for the 9s? But yeah, this 99 down to 11 was an approach I did consider at a later stage as well.
Yeah. Which, of course, by the way, I mean, I assume a lot of all y'all out there are already familiar with this, but as also the nice little inlay hints that I have enabled indicate, this just allows me to iterate downwards, which is kind of cool, like going backwards in a quite convenient manner. I also one of my favorite little trivia points is that in Kotlin we have this like digit to char, which is a different function than to char, which is important to note. I don't know. Are you in the camp of calling it char or car or care?
Char. I call it char. I also at a later stage tried using a digit to char. Yeah, I remember chasing errors before I knew about digit to char, because if you use to char, then weird things happen and it's not what you think. And those inlay hints are really invaluable for making the off by 1 errors less.
Oh, yes, right? 100%.
Because it's 7 morning somehow off by 1 errors are just like the chance that you're going to hit it off by 1 error if it's before noon is just so much higher.
Oh, absolutely. Like totally. But yeah, so the difference between digit to char and just to char is that to char does the interpretation as like an ASCII character. Like it just moves it into like a char, into the char range. Versus digit to char specifically like looks at the number, like might be a 7, and then gives you back a 7. Notably, digit to char is only available from 0 through 9 because anything else cannot really be considered a digit anymore. And the same way also goes the other way around, I believe. So if you have like a character, you can once again say to int, and we have a deprecated version called digit to called to int, because this one again it was kind of like ambiguous. So instead we have digit to int here.
So did you also used to do that trick where you deleted, you went to char and then you deleted the value of 0, or I think it's 30. You delete 30 in ASCII. If you do to char and it's not digit to char, the number you get out, you always have to subtract a 30 to get the actual number. That was in the days before we had the digit to char function.
I always remember the trick with like subtracting. Was it subtracting a space? I think it was subtracting a space or adding a space. What like this like depending on the direction, this converts lowercase to uppercase and uppercase to lowercase letters if they are individual characters. Yeah. That's the part that I still remember. But yeah, the otherwise you still kind of have the trickiness. Luckily, while I used to we used to have all these kind of tricks, or you write them out as an extension function once or twice. Now life is a little bit easier. Yeah, no, very nice. I think that concludes part 1 pretty well, right?
Yep.
Well then we'll move on to part 2 here. Oh, actually, there's one more interesting point here, but I'm not gonna bring it up yet. I'm gonna bring this up later on because it will become relevant. But I love this comment of I went on an hour walk through 0-degree weather because part 2 annoyed me so much. Okay, let's find out what part 2 has in store for us here. The escalator doesn't move. The elf explains that it probably needs more joltage to overcome the static friction of the system, and hits the big red joltage limit safety override button. You lose count of the number of times she needs to confirm, yes, I'm sure, and decorate the lobby a bit while you wait. Now you need to make the largest joltage by turning on exactly 12 batteries within each bank. The joltage output for the bank is still the number formed by the digits of the batteries you've turned on. The only difference is that now there will be 12 digits in each bank's joltage output instead of 2. Consider again the examples from before. With a 987654321111111, the 8111119 234 234 234 234 278 and 818181 9111 2111. Then the joltages become much larger because the largest joltage in our first number can now be found by turning on everything except some ones at the end. So 9876543211111. In the digit sequence with all the ones in the middle, the largest joltage can be found by turning on everything except some ones in the middle. So 8, a bunch of ones, and then 9. In the 234 example, the largest joltage can be found by turning on everything except a 2 battery, a 3 battery, and another 2 battery in the start to produce 4, 3, 4, 2, 3, 4, and so on. And in 818181, the joltage with the prefixes of a bunch of 8s and 9s is produced by turning on everything except some 1s near the front. So the total output voltage is now much larger. Indeed, it is quite enormous. And like that, we go from 2 problems to 12 problems, and I think the real thought that we should all be having by this point is what was commented earlier, which is it's an escalator. Why don't we just walk down? How long is this escalator that we can't just walk the steps? I think this is the real. I think that's the real answer. But I don't think. But we still need those stars, right? So Maya, what went through your head here?
Okay, so like walking the escalator, there's certain things in code that I don't like doing so much, and I was trying to avoid that at all cost. But we'll get to what those are later. The first thing I thought was, let me just brute force this.
Okay.
Right?
Yeah.
So take my existing solution and just make it be for 12 digits. So will you share my screen quickly and I'll show you something?
Of course. Here we go.
I didn't do this, but I was tempted. I just, for a little bit, I saved it in a Scratch file just to show you. The second thing I thought was, the same trick about 99 down to 11.
Mm-hmm.
I can do that. 9 down to 1. Let me try and do that. Of course, I saw that it was running for a little bit longer, and I decided, no, that won't be either. And why was this the thing? I mean, this took me like forever, and I also had to go for a walk before I figured out, because I don't like coding recursions.
Mm-hmm.
I know I have to be able to do them, but I hate doing them. They mess with my brain. So if I can avoid coding a recursion, then I will. I will almost be prepared to write this Christmas tree before coding a recursion. But in the end, I did end up solving the problem. What I can show you here quickly, the splitting up of things are very similar. But what I have here is lots of mental churn of like, this is some of the things I tried, and for some other reason, I misread the puzzle. I knew there could be gaps, but then the one solution I coded up and got the wrong answer was because for some other reason in my brain, I thought there couldn't be gaps in the second one. So I had to reread the puzzle. It's all of the same things that are always happening in Advent of Code. And so I had to start all over again. And then I had some ideas of like, this is like me trying to figure out exactly what's happening next and what's happening first. And the other thing it is like, if you've built a nice data structure like that list, that map with the list, it's like, I want to use that, right? Like I want to go and use that now. But the solution doesn't need that. And if I want to try and use that thing in there, it just makes the solution much more complicated. So I started from scratch. So let's close these regions and I'll show you quickly. After I
love though, sorry, I really love this. It's very real. Like that's very good because It's
and so even, at this point I couldn't even think of good function names anymore, right? Like so this find max big joltage, which is part 2 joltage. The input is much the same here, except now I'm not even switching out or split. I'm just passing in the string straight into the find max big joltage, and out of this should come a number. And I'm going to sum these, okay? Mm-hmm. And then the find max big joltage, it's actually pretty simple in the beginning. It's if you do a recursion, you need to have the point where everything starts, where you put everything in, you feed everything into the recursion. And here it's the string, which is the string of the bank string. The number of digits, which in this case is 12, because that's how many we want. And then I ended up carrying this max string, which it's the maximum number that I'm busy building up along the way. Mm-hmm. And then this next biggest is the interesting part of the whole thing. And it's just, with all recursions, you need to know how to break out of that loop. So you need to know, if I'm at the bottom, if I'm on position 0, I need that max string that I've built up needs to be along, pop it back up. And then this, I'm matching from 9 down to 1 again. There I'm getting the character. And then I've got this valid candidates method, which goes through the list and sees if there's a valid candidate that it can use. We can look at that for a moment. See, I did use my build list again.
I love it.
It's just looking for that character in the bank. And it knows how far along we are. Are we at 12? Are we at 11? Or are we? And then it finds that digit, and it only adds digits that it finds in the bank of strings if they are the right amount from the end of the string that you're looking.
So this is the point where you make sure that you still have enough space to make a full
12-digit number. Exactly.
Okay.
So I get the valid candidates. So these are all the 9s in the big string that potentially have 11 neighbors that could be. Now I just have to figure out which of these ones is the biggest one. And for that, if I get candidates, if there are a bunch of 9s and they have got 11 neighbors or 11 string characters after them, I just call this next big thing again, but this time skipping one further. So I skip over the 9 I've just found. And the position is now not 12 anymore, it's 11. This is important because if you don't do this, then it won't ever fall out of here. And then you chase your tail and get the wrong answer anyway. And then I just pass the max string that I'm accumulating through, so that when I get to the 0th position here, that I can pop the max string back out. And then here, this max or null, just like of all of those, picks the biggest one.
Okay, yeah. So you're looking, you're recursively going through all the candidates. You're kind of like building the sub number trees, and then out of those number trees, you're picking the one that is the best sub number tree, and then effectively, as you bubble back up, kind of like pre-pending whatever you had before.
Yes, I'm sure you could do this with a fold, but that would have really broken my brain.
Very cool. Very nice. Out of curiosity, do you have an approximation of how, or do you have a feeling for how long this runs? Because
a long time.
Yeah.
It takes long. Well, I mean, I can quickly run the whole thing, and we can see.
Sure.
Yes. Let's see if I can run this. If this will run. No, it doesn't run like that. You need to run it like this for some other reason. Run. Okay, so the part 1, okay, this is not repetitive runs. This is just the millisecond thing. Part 1, there, okay, 9 milliseconds for the part 2 test values. Part 1, 30 milliseconds, and they're here 1.3 seconds.
All right. Okay.
It could probably be optimized. It could probably go better, but a star is a star.
Exactly. It's all about getting those stars. That's what matters. I really like this solution. It's really cool. The recursive approach, it makes a lot of sense. It's effectively, I mean, the best part about this is that it's an approach that you could pretty much do even if the condition changed in like a hypothetical part 3, because you're already building like all kinds of combinations, like you're already building those subtrees. So like adapting that algorithm would in theory be pretty smooth. I do.
Now, if I'd only done the recursion for part 1, I could have just changed the 2 to a 12 for part 2, and it would have been a snap like that.
That is very true, but then you would have probably given up some precious time on that original version. Like this is always I think one of the very interesting parts about Advent of Code. You can try to guess what part 2 is going to be about, but Mr. Vastel has been known to throw a curveball or two. Like sometimes, the number just gets bigger, but sometimes it's a complete reinterpretation, and then might not be exactly worth it. So it's a trade-off. However, I do have a solution that I think is worth comparing. Before we look at the solution, I also want to share a picture here that a colleague of mine sent me. This was him setting up his the brute forcing approach and noticing that after allocating about 96 gigabytes of memory, that probably creating all combinations of a 100 character string, which is like somewhere in the 150 trillion range, is not particularly feasible. So there has to be a better solution. And yeah.
So what's your time threshold for when you brute force and it doesn't go through?
20 minutes.
Okay.
I will be very honest with you. I don't know which year it was, but there was one year where I think I did some like I had a pretty silly solution. But I could tell that it was making progress, it was somewhat making progress, like, noticeably, and most importantly, it was not slowing down. This is always the tricky part, right? Like in a lot of these algorithms, the tricky bit comes from it becoming slower as it progresses. But this one wasn't slowing down, so I ran it, and I was still doing it like in bed at 6 a.m. And I got up, I brushed my teeth, I took a shower, I came back, and I had a solution like 20 minutes later. And then I was like, okay, and now that I'm like refreshed and I'm ready, now we can go for a like nice and slightly more clever solution. But again, all in the name of getting that star.
Yeah.
Yeah.
With the leaderboard, the big leaderboard not being there, I think I'm more prone to carefully thinking of something. But
Yeah.
for today, I had so little time. I had to just like do something. So
No. I mean, honestly, so I think if I have a solution that runs in like 2 or 3 seconds, I'm typically more than happy. I might still kick off a discussion to see if I can be more clever, but that's already pretty great. So for this solution, first of all, of course, at the end of the day, we just need to find that 12 joltage level, and we want to sum it. This part is particularly uninteresting. Here's what I do. The key approach that I had to this problem was thinking about how would I want to construct this number, right? And the answer is, well, ideally, I'd like to have a 9 and then like 11 other characters. And if I can't have that, I'll have an 8 and like 11 other characters. Which means I need to find a 9 somewhere in the range of my string so that I still have at least 11 characters remaining that can fill things out afterwards. So this is effectively what I wrote here, right? So I said, okay, I want to build a number string. I'm starting at index 0 inside my bank, and then now I need to fill my number string with 12 numbers. So we'll start with 12, right? Or we'll start at the 12th position, and effectively this is just off by one thing. But in the first iteration, I need to find 11. Like I need to leave 11 digits standing, and then I need the biggest number to the left of that. So this is my little function that I have here. I went with the full enterprise naming. This is find largest digit in bank with at least n digits remaining. Mm-hmm. And it doesn't indeed just take the bank. It takes the start index from which we start looking, and it takes the required remaining digits. And then the implementation for this is, first of all, we do a sanity check to see that we are actually looking inside the string. This is just because I still make off by 1 errors. And now I do something quite similar to what was in the first part, which is I look for a large number, preferably a 9, but I'll also take an 8 or a 7. So I'll see if I can find a 9 or a large number between inside my bank, given whatever numbers that we had already looked at, like that we had already stepped through. If I can't find one, we'll pick a smaller number. Otherwise, and again, this is the part where it's really easy to get an off by one error. We still need to make sure that the position of this number leaves us enough digits to still construct the full number, to construct the entire sequence of 12 numbers. Of course, this is going to like decrease as we loop, right? So by the end of it, we only need to leave 1 digit, and then at the very end, we only need to leave 0 digits because we will have constructed our entire thing. So if we found a number that is in the right range, kind of to the left-ish, and again, since we go down from 9 to 1, we grab the largest one, then we just return it. And we go back, we add it to our number string. So like we append it, right? We build it from the most significant digit to the least significant digit. And we just move our start index, so the numbers that or the indices that we're looking at, one after where we've just found a digit. So this is kind of the overall approach, which means in total, we are just 12 times finding an individual digit. For each one of them, we are looking at things for 10 times. So if we run this, it actually runs faster than my part 1 implementation. This runs in 6 milliseconds because all in all, it doesn't have to do much more than a couple hundred iterations. It was also one of those great scenarios where I could show off something that someone asked earlier, which was, why wouldn't you just use a char with a range? I couldn't do this in the first part because there I was going from 99 to 11. But here I'm going from 9 down to 1, which means I can also just go from character 9 to character 1, and it works the very same. So both of these are the same approach. And by taking this approach, one of the other things is also true, which is that, yeah, with this approach, we can now find out that rather than going from 12 down to 1, we might as well go from an arbitrary number, which for part 1, it would have just been a 2. So this solution can also be used to solve part 1, but that would have been a spoiler. So yeah, this is kind of like the solution I came up with. I came up with the idea of this semi-quickly because, again, it really just does kind of describe what I would do if I tried to do it on paper. The actual implementation of making sure I get all my minuses and all my plus ones and all my like greater than and not like greater equals signs correctly, I'll admit that took a couple of minutes. But yeah, this is kind of how I solved this bit.
Yes. I think it's lovely because it has no recursion, right?
Exactly. This is actually the part that I was also like, Maya's gonna love this one. Yeah, because I thought about doing it with a recursive approach as well. But then I was like, I had the same reaction as you. It also does. It just makes things a little harder to think about sometimes, or a little harder to reason about.
And to debug, right? Because you have to go down and up and down and up and down and up those and remember where you are.
Indeed. So besides doing a little bit of index math, this turned out to be a fairly straightforward solution. Luckily.
And also, I like the fact that under pressure, your function names become longer and mine become shorter.
Oh, absolutely. I've had this. Like originally, I think I was also someone who loved doing the short names, but I find that the harder I have to think about something, the more I rely on just literate programming, like just writing down what happens and writing a whole bunch of comments saying, okay, now this precondition was cleared. Now this is the case. Make sure we don't drop the wrong number. Make sure we don't double count. Like there's a lot of this kind of stuff. Also, this, I'll be honest with you, I think the function name originally was even longer. I think in another version. Yeah, originally it was find largest digit in bank so that there are still at least n digits remaining, which is that was maybe slightly silly, but
And my original version for my recursive function was BB.
that's also very good.
I couldn't think of it.
Yeah. No, it's for me. I quickly arrive at the breaking point also with the with primitive obsession. Like when I start having like a map of a list of longs or something, I like of long to list of long. I immediately, or I very quickly start confusing myself, and oftentimes those, like, investing that upfront part saves me a couple of brain cells that I very desperately need to solve the problems themselves.
Pairs, right? Like if you have those pairs of pairs, and you have to remember which is the first and which is the second, and which is the first and which is the second.
Yeah.
So then it's like quickly you need a data class.
Oh
to
yeah.
remember the things.
So that's having just having something to hold on to is so much more convenient for me. I hope that I can still get it into my fingers to also write more like value classes to like wrap things there. But the data classes I got down quite well, and I do also just appreciate the destructuring syntax there again for like quickly pulling out the digit and index again, all these kind of things. Yeah, very good. Awesome. Well, I think, let me just check here if there's any more comments. Someone mentioned that they also had a stack-based solution, which sounds really cool. I've also seen a stack-based solution online, but this one I have a lot harder time intuitively understanding. I think it's a quite similar approach, but I find, again, if I have to reason about it and I have to explain it, this approach is like a little nicer for me. If any of y'all are interested in finding out more about the different types of approaches, please make sure that you also head on over to the Kotlin Lang Slack, where we always have the daily threads where people are posting their solutions. And some of them, to no surprise for anybody, some of them are much shorter than the solution that we've constructed here on stream. Some people are really good at the golfing the code down to making it very short. Some people are very good at making the code very, very quick. Depends on what you... Some people are really, really good at making it really readable. And some people, like me, just get to show their code on stream. It's somewhere in the middle. We get to comment about it and have a good time. But yeah. No, I'm really glad. First of all, it's really cool that you managed to find this recursive solution for part 2. And I'm really glad that we could explore that today, because it's if anything, first of all, I'm sure a couple of folks in the chat have also approached it recursively, but it's probably also a good warm-up for the upcoming days, because there's no way Eric is gonna let us go without something that requires recursion in some way or another.
Yeah, definitely. So at least now I know I can actually code it from scratch if I have to. When put under the gun or put under pressure, I can actually pull it off.
Yeah.
Just have a stream looming, and then, yes, I can do recursion.
Exactly. It's the number one productivity hack. Yes, and of course, for our super enthusiasts about recursion, I once again want to remind all of you about the existence of the tailrec modifier in Kotlin, which also helps. Let's see if we have a... Probably this one is a nice description. Yeah, the tailrec modifier, which allows you to specifically have a tail recursive function, so one that simply returns either a base case or another function call directly, and it allows the compiler to unroll it into a loop, so you don't have any stack overflows, which is really, really cool. So that might be coming up. Who knows? Just something to keep in mind always. It's always something new. And yeah, here we see Johnny mentioning that tailrec was super helpful once or twice last year, which is great. That's excellent. All right. Well, Maya, it seems that we have once again gotten a little closer to not saving Christmas, but at least decorating the lobby. So thank you very, very much. More stars for everybody. As usual, my question to you is, what is the prediction? What do you think might happen tomorrow?
I don't know what's going to happen tomorrow, but my wish is for one of those little computers that do things. You know, when he simulates a little computer? Oh, I like those best. Those are my favorite ones. But we probably will get some other wandering around lost in a snowstorm style Dijkstra vibe or some other graph traversal. I mean, there's bound to be one of those, which is the other thing I don't like doing.
Yeah, those can get tricky. I guess we'll only... Yeah, the good part is that we will only have to wait 10.5 hours to find out what the actual truth is going to be. I really like the concept of like the snowstorm. Like the puzzles... There's one category of puzzle which I think is very strange, which is these like the simulation puzzles. Like you have a bunch of particles and then they all either interact with each other or they have like some center of gravity that they fly towards. And those are always the ones that I think are the trickiest, are the ones where they say like, what do the points spell out in like 2D or 3D space? Or
that Christmas tree, where you had to watch and then see the tree appear out of nowhere, and that was the thing. Yeah,
that was wild. So whatever might come, I'm mentally ready for a curveball, whatever it might be.
Yeah, but I mean, that's the most entertaining thing about it, because you can complain about the curveball on Slack or on Reddit.
Exactly.
Or watch other people's memes about the curveballs.
Exactly. Yeah, so the graph before simulator is one of the predictions. The other point here is that, didn't I have a browser extension that always shows JetBrains on the side? I did, but back then I think I was still using Chrome. And now with Manifest v3, I'm on Firefox. So probably we can update the extension. I don't think it does much. Probably I can just throw in a user script. If someone wants to send that to me on Slack that does not contain a credential stealer, I will be vetting the code. Then you're more than welcome to. Otherwise, we might get to that as well. And we'll see what we can do. It's a good point. All right. Well, let's see what kind of curveballs we have expecting us tomorrow. Thank you so much, Maya, for joining us today. It was really lovely.
Pleasure. It was lovely. Thank you.
And of course, thank you to everybody who decided to tune in. As usual, we have 2 more streams coming up, and you will not want to miss them, because both tomorrow and the day after, we have really wonderful guests who are... I don't want to name them directly, but let's just say that they are renowned for their ability in explaining, in live coding, in visualizing. So, should be very fun. To not miss them, make sure you hit the notify me button right here on those 2. Make sure you also subscribe. I don't think I even ever said this before. And if you want to have more experiences around Advent of Code in Kotlin, you, of course, simply head on over to our blog post as usual. Thank you so much for joining us today at the slightly later hour. And I very much look forward to puzzling alongside all of you again tomorrow morning. So thanks for tuning in, and take care, everybody. See ya.
Bye.
Bye-bye.